Thank you for the introduction. So it's a joint work with Meng Wu, my PhD student, and a collaborator Chris Eldred from the Sandia National Laboratories. And so the goal of this talk is to show some recent results on geometric formulation for fluids with open boundaries. So as you know, the case of the geometry of fluid in a container, the fluid that slips on the boundary is well known, right? It's the Arnold approach. You consider it as a dynamical system of diffeomorphism groups. But once the fluid can go out of the domain, like it's happening a lot in a lot of situations, all this approach breaks down. So we are, for various reasons, we were interested to see how we can find some geometric structure behind these open fluid problems. So to give an overview and some motivation, let me just recall the standard situation of fluid on closed domain. So this is due to the geometric description of Arnold. So why is this geometric description interesting? Because it gives rise to a lot of other structures that are then useful for various reasons. For instance, once you see fluids on diffeomorphism groups, then you have access to variational formulations in the type of Hamilton's principle that you can apply reduction by symmetries to find variational principles in other descriptions. You have also access to the whole geometric structure on the Hamiltonian side, such as quadrant orbits, Poisson brackets, etc. Also, as we have heard earlier, it's very useful for numerics and for modeling. So the goal is to see what can we say in situations like this, in which the fluid can flow in or out from the boundary. So this happens, for instance, if you do meteorological applications, but you concentrate only on some regional area, right? You don't want to describe the whole dynamics on the whole globe, but just on some specific region of interest. So what do you put here in the boundary? What boundary condition do you put? Are you assuming that you know them or that simply it's unknown? So all these questions are very important when it comes from when you arrive to numerical simulations. You want to derive some good schemes for these problems. Okay, so so I review first the situation of closed domain. Then I will proceed to the case of open fluids, and you will see that the goal is to attach this to a first principle. That's our goal, right? We want a first principle from which we can deduce everything else. So our first principle will be Lagrange d'Alembert in our case. Okay, so let me quickly recall, maybe you all know this, but how the geometric formulation of fluids is arise. So you have your fluid, right, in a domain omega, and the evolution of the fluid is given by a curve in the group of diffeomorphism of your domain. And by saying this, you already impose that the fluid is closed, right? The boundary point stays at the boundary. So fluid cannot escape. And the Lie algebra is the space of fluid velocities. Then you apply Hamilton's principle to get the equations of motion. So here I consider compressible fluid. So my Lagrangian is defined on tangent bundle of the diffeomorphism group. And it has these kinetic minus potential terms, like we have seen earlier in the shallow water equations. Here you simply choose your preferred energy function in terms of the mass density, and we have this strange appearance of the Jacobian because I'm working in the Lagrangian frame. And for me it will be very important to distinguish between the integrated Lagrangian and the Lagrangian density. This is crucial for the case of open fluid, but so far it's just the usual case. Then equations of motion in the Lagrangian frame follows from Hamilton's principle, in which you take variations with respect to all possible variations of your diffeomorphism groups, and you get your equations in the Lagrangian frame. Now, if you want to have this in the Eulerian description, the easiest way is to just change the frame and compute the variations that are induced in the Eulerian frame from the free variations in the Lagrangian frame. So here you have a more usual way to express the Lagrangian, right? Kinetic minus potential. And your previous Hamilton's principle becomes now the Euler-Poincaré principle on the Lie algebra of the diffeomorphism group, right? In which you don't consider arbitrary variations, but only variations that are induced from the free variations in the Lagrangian frame. So they have this form, right? Either you compute them directly, or you apply this Lagrangian reduction process on Lie group, and you get them. So you get here the general equations. You get the barotropic fluid equations in my case because of this choice of Lagrangian. But in general, you have this formula for arbitrary Lagrangian density. You pass on the Hamiltonian side and you get the Lie-Poisson structure. Okay, so now let me see, we keep this in mind and try to guess what can we do to adapt this when the fluid goes out from the domain. So first, we still have a domain of interest, which is not moving. We have a domain, right? But now the fluid can flow out or in, or on some part of it, maybe it cannot, but some other part it can. So we cannot use the diffeomorphism group, right? It's too restrictive. So let's say we take the diffeomorphism of the whole space, even if this seems too big, because we don't need all these diffeomorphisms. Let's consider this. We will see it works, but for now it seems big. We still take the same Lagrangian density as earlier, right, that characterized the fluid. And now we build this Lagrangian, the integrated one. So the integrated one is defined on this big diffeomorphism group, and it also depends on densities defined everywhere, but you integrate only on the labels of interest. So remember that these big X are labeling the fluid particles. So I want to integrate only on those fluid particles that at the current time that we are living are in the domain, right? So these fluid particles of interest, they currently belong to the pre-image of the domain of interest, right? Is it clear? Because it's the main change at this step for passing to open fluid, right? So we integrate only on phi minus 1 omega, but we integrate the good old one densities of the fluid, right? So this is just to illustrate what happens, right? In this case, for a pipeline or a tube, in which there is inflow and outflow, right? So this is step one. Step two, we know from first principle in mechanics that if there are forces to be added, considered as external force, not as internal dissipative force, this would be something else, then we have to use Lagrange-D'Alembert principle. So in which you take the Hamilton's principle, but you add the integral of the virtual work of your external force on a variations of your system, right? And you get the equations, the Euler-Lagrange equations with external force. And so we want to apply something like this. So I will restrict to two kind of not force, but flux in my case. Related to the fact that the fluid is open first, I allow a boundary force associated to the fluid momentum, because the fluid can go out or in, so it transports some fluid momentum. But also, since it is compressible, it also transports mass density, right? It's very possible that mass is leaving or entering the fluid flow. So we need an additional scalar field, F, whose variations can be put here to be combined with some boundary force that we don't know yet. So we need some new variable scalar field F to be added. And it turns out that this F is also needed to impose these continuity equations on the mass density, which we didn't have to do it earlier because we were simply in the usual case of a closed fluid, right? So we keep these two ingredients, and we can build this following Lagrange d'Alembert principle. So first, the action functional, as I said, is integrated on this domain, but also we add rho times f dot to include the fact that rho dot is preserved. So we add like constraints indicating that rho dot is constant, rho is constant. And in the same times, the variations of f will be used in this part to impose the boundary flux in mass that we need. So with a bit of geometric thinking, we also have to devise what are the boundary force, what geometric object we need on the boundary to impose this boundary force. So first, concerning the fluid momentum, we will need a map going from these labels to T star Rn because we have to pair with variations. And then we need a volume form on the boundary because we have to integrate on the boundary. Same thing with, this is for the fluid momentum. Same thing for the mass density of the fluid. So, right. So at the end of the day, what we propose is this type of Lagrange d'Alembert principle, in which we have the usual Hamilton's principle term with the big difference that we have a moving domain here, and a virtual force term of d'Alembert type, also on these moving things, but on the boundary, right? Not in the inside, on the boundary. Right? So now we want to go to the Eulerian frame. So as you know, to go to Eulerian frame, we have to assume, and it's always the case, at least for this class of fluid, that the Lagrangian has some invariance. So the Lagrangian density, for instance, has this so-called covariance, in which if you compose everything by relabeling the fluid, then you get the same answer up to a volume contribution here. But you have to assume also the same thing for the force. So these are the technical formulas, but you can guess what they are, right? You just assume that the quantities that you have are covariant with respect to diffeomorphism of your label space, not the diffeomorphism of your fluid, right? And doing the Euler-Poincaré reduction, you get this reduced form of the variational principle. So you recognize here the usual Lagrange Euler-Poincaré variational term, in which we have plus rho f here. We have seen this first term in the shallow water equations in the first talk. Now we have this additional term, and we have the boundary contribution. So the only difficulty here is to identify what are the variations of the variable to be considered here, right? So this is the good old one, Euler-Poincaré variations, but you have another one here coming from the reduction process. But the variation of mass density is now free, right? So here is the proof of how we get this from the Lagrange d'Alembert approach. So if you want to know more, I can go to the details. But this is the usual approach, but taking account of the fact that the domain itself moves and that you have also boundary things moving around here, right? So if we apply this, we get this type of equations. So at the interior of the domain, no surprise, you have to get the previous equations, right, that are valid at each point at the interior, but you get now this form of boundary terms. So this is the boundary condition on the fluid momentum, and this is the boundary condition imposing the mass flux entering or flowing out of the domain. So it turns out that these equations, as simple as they look, they give a lot of insight about the modeling of the fluid, because there is a lot of confusion that can happen if you have, for instance, the barotropic fluid. DLDU is just rho u, so it coincides with this one. So it's not clear what boundary condition we really have to implement for our modeling. But this gives really the right, the consistent expression of the boundary condition that is consistent with the, for instance, energy balance of the system, right? You want that the things that goes out really matter in the right way on the energy balance. Same thing for the mass contained in the fluid, right? So this is illustrated here in this formula, right? In which we can evaluate precisely the evolution of mass inside and the evolution of the energy, the total energy inside the volume, which is no more zero, right? For instance, and this I know from my collaborator Chris Eldred, when devising models for regional climate predictions, for instance, in which you have the rotating shallow water equations, it's very hard to design physically consistent boundary condition, because you have several terms in the Lagrangian, like the Coriolis term or the other Green-Nagdi terms or other approximation terms that makes this DLDU fluid momentum very different from just rho u. But this approach gives you exactly the right combination to be put in your model. So this was, in fact, the motivation for what we did. So let's see what happens for the case of barotropic fluid. So DLDU is just rho u in this case, so you get this type of boundary conditions. And as I said earlier, the diffeomorphism group that I choose seems too big, right? It's Rn, it's too much bigger than what we really need to know, right? So is there a way to appropriately choose J and J to recover the closed fluid case, right? So yes, if for instance you assume that J is 0, so the fluid is now forced to stay inside, and because of the consistency between the two formula, you must now take big J, the flux of fluid momentum, to be 0. So you can be surprised that now the boundary conditions for the mass density has just disappeared, but it is exactly consistent with what happens when we are when we have a fluid in a closed domain, right? There is no boundary condition for mass density on the boundary for well-posedness. We don't need to say anything about rho on the boundary when the fluid is closed. And now another case is that if this quantity never vanishes, for instance, then you have now two boundary conditions, which is consistent with the physics of open fluid, in which when the flow is coming in, you have to, in addition to the boundary condition of on U, you also have to have another boundary condition for the mass density. So it's completely consistent with what is needed. So I think I have to conclude, but I just wanted to make a comment about the Poisson side, because there has been some proposal how to extend the Poisson bracket formulation from closed fluid to open fluid in Oettinger in 2006. So his idea was to work a bit in an ad hoc way, right, and to compute a Poisson bracket, or a bracket that would yield the correct equations for an open fluid. And so his idea was to integrate out all the terms in the Lie-Poisson bracket that are on the boundary, and just to say that this term is 0. So what remains should be the bracket for open fluid. Yeah. So this is a first attempt. It's not totally satisfactory, because this just gives you the fluid equations without boundary conditions. Yeah. And what remains of the Poisson bracket, which he calls the bulk Poisson bracket, is not in fact a Poisson bracket on a domain with boundary. It's only a Lie Poisson bracket on a domain without boundary, which is not totally consistent with the fact that the fluid, although it is open, it's still on a domain with boundary, right? So our proposal is a bit different, right? We have the Lie Poisson bracket, which is really a Poisson bracket on manifold with boundary, right? We can check Jacobi, but we have a boundary contributions that allows one to exactly say what are really the boundary conditions in the fluid domain. Okay, so this is what I wanted to say. This is some conclusions, what I did. So as I said, we want to use this for numerics, right? Now to have the correct balance of energy and mass between the inside and the outside of the domain, like we have seen in the regional simulation or in the wind turbine experiment. And there is a lot of interesting structure behind this, like Dirac structures that can also provide these boundary conditions in the same way as I presented here. Okay, thank you.
Thank you very much, Francois. One question here.
Thank you very much, Professor. One question. As you, shown in the slides, you proposed the continuous time formulation in the Eulerian framework. And is it possible to study the discrete symmetry, reduction by symmetry? And what's the possible influences in this discrete setting? Thank you.
Your question is, can we mimic this in the discrete case? The reduction process? Yeah, we can do this. Yeah, but by replacing this, you have seen a bit of this in the first talk, by replacing the diffeomorphism group on which the fluid evolves by some finite dimensional Lie group analog, and by implementing this variational principle in the same way, but in a finite dimensional setting, and you will get the variational discretization of the open fluid system. Yeah. Is this your question?
Yes, and what's the possible influences in this discrete setting? Is it the same as the continuous time setting?
Yeah, the reduction is the same flavor. Reduction works for all Lie groups, so it works there and there. But the main advantage is the balance of energy and mass between the inside and the outside. This is a critical point for numerics, very important. Yeah.
One last question.
So you mentioned that the variations of the mass density rho were unconstrained, right?
Exactly.
But you still get the right mass conservation law. How is that possible?
Because I added, yeah. It's a subtle, so the mass density equation stays the same inside, right? It's rho dot plus div rho u equals 0. But now we have a boundary condition for rho. So it's no more true that rho is acted on by the diffeomorphism of the fluid domain. This doesn't hold anymore, because I have changed the boundary conditions. So we can no more say, like here, let's fix rho, and we don't see it here, and we have just Hamilton's principle. We cannot say that. We have to accept that rho lives in itself, has its own dynamics, but we kill a bit this by adding this term here, but not completely, because we allow something on the boundary here, because this flux, right? This is the story, right? So we impose here that the mass is preserved inside the domain, but it's not totally transported by the diffeomorphism, because we have this Lagrange-D'Alembert term that involves the variations of F, and F is the companion of rho.
But the mass conservation is implied in this term, rho.
Exact, yeah. Yeah, it's a subtle